Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in University of Delhi's Chemistry Department. Today, we are going to discuss about the module Electrochemical Scanning Tunneling Microscopy, wherein we will deal only with the introduction part. This will be under the paper of Surface Analytical Techniques, Part 1. After completing this module, you should be able to understand the first part about what is it. That is, one would be able to understand the definition of this. After this, you will be able to get the introduction of this topic, that what it deals with. Then a little bit about historical background in terms of who invented this and who did work on instrumentation pertaining to this. And lastly, we shall be talking about the applications which one uses this instrument for. Now, when we come to the first part, which talks about how do we understand what is it, that is in terms of definition, we know that electrochemical scanning tunneling microscope, which is abbreviated as ECSTM, is a conceptual and instrumental extension of scanning tunneling microscope towards its application to charged solid-liquid interfaces. We also have these in electrochemical systems primarily. So electrochemical reactions occur in electrolytic solutions, and in the interfaces we use this. For case of electroplating or etching, as we know, or batteries for that matter, and so on, we use this very effectively. On the electrode surface, many atoms, molecules, and ions absorb and affect the reactions. Now, what way do they affect? What way do they get absorbed? All these can be studied once we use this. In the past, in order to get a clear understanding or information about the structure of electrode surfaces and reactions, it was never clear what way they go about, but with the help of STM, the sample electrode can be put to this, and this was taken out of the electrolytic solution and measured under ultra-high vacuum conditions. In this case, the structure of surface changed and could not be investigated very precisely. By using this microscope, however, these problems have been resolved. The scanning tunneling microscope, STM, as I said, is abbreviated, and the atomic force microscope, which is AFM, both at times are used in unison, are scanning probe microscopes capable of resolving a surface or the details of the surface down to the atomic level, which is an extremely low level to understand. The potential of these microscopes for revealing the details of the structures is illustrated by atomic resolution images, including that of graphite or an organic conductor, an insulator, layered compound, and individual adsorbed oxygen atoms on a semiconductor, of course. Applications of the STM for imaging biological materials directly has been hampered by the poor electron conductivity of most biological samples. The use of thin conductive metal coatings and replicas has made it possible for us to image some of the biological samples also, as indicated by recently obtained images of a record DNA complex. A phospholipid bilayer sample or an enzyme crystal, for that matter, have been investigated with the help of this STM. The potential of the AFM, which does not require a conductive sample, is shown with molecular resolution images of a conducting or non-conducting organic monolayer and an amino acid crystal that reveals individual methyl groups on the ends of amino acids, which otherwise is very difficult to do. Applications of these new microscopes to technology are demonstrated with images of an optical disc stamper, a diffraction grating, and a thin film magnetic recording head, and of course a diamond cutting tool in this. The STM has even been used to improve the quality of diffraction gratings and magnetic recording heads. One can know how sharp or how properly they are working with the help of STMs. Here we have been talking about scanning electron tunneling microscope, and the introduction of this would be to start with what is tunneling and how does one go about it. Tunneling is an electrochemical experiment that takes place in an electrically conducting environment. The electrolyte, which is normally aqueous or organic or ionic liquid, for example, which is used here, electrochemical reactions may occur at the very tip as well as at the substrate. This is what one finds in the introductory part of this. We'll deal with what will happen if we pass the current, and the results of that would be shown in what manner. The resultant electrochemical current IF is superimposed on the tunneling current IT. Now to minimize IF, which is the resultant electrochemical current, at the tip relative to IT, the tip is coated with an inert and insulating layer made for this purpose, for example, of glass, a piezo, or polyethylene, or electrophoretic paint material. The remaining electrochemically active area of very well insulated tips amounts to 10 to the power minus 8 to 10 to the power minus 7 centimeters square and yields residual electrochemical currents of typically less than 5 picoamperes, which do not interfere with the tunnel current of 0.1 to 10 nanoamperes. We'll talk about the functionality of this technique. The functionality is controlled by a biopotentiostat, which represents a potentiostat with two independently adjustable working electrodes. So this is a typically 4-electrode potentiostat, which is used here and is termed as a biopotentiostat. Now the choice of tip material, which is very important, and potential ET are dictated by the request of high mechanical and, in addition, chemical stability to minimize the Faraday current IF we put it at the tip. Atomically sharp tips are typically prepared by electrochemical etching of thin film wires such as tungsten, platinum iridium, or gold for that matter. The choice of the RE depends on electrolyte and electrochemical probing or electrochemical problems under study. Mainly, this equipment ECSTM setups are capable to perform scanning tunneling microscopes or scanning tunneling spectroscopic measurements. The latter are carried out at fixed lateral positions of the tip above the substrate. In current distance STS, that is scanning tunneling spectroscopy experiments, the tunneling current is measured at constant ES and ET as a function of the vertical tip displacement, that is delta Z. Well, when we look at the kind of potential which has to be given at the tip or the conditions that are to be maintained for getting the right kind of images, one has to have independent control of the potentials of both tip and substrate with respect to the RE that allows various modes of current voltage spectroscopy in an electrochemical environment. That's important. In variable bias scanning tunneling spectroscopy, or as it is known as STS, in this mode, the potential of one electrode is fixed, while that of the other is swept over a wide range of potentials. This regime is equivalent to an ex situ current voltage scanning tunneling spectroscopy experiment with two electrodes. The constant bias mode of current voltage STS is unique for the electrochemical environment. Here, both ES and ET are swept concurrently so that their difference EB is kept constant. This is one of the important features of this technique called STM. Historical background of this technique is given. The application of the scanning tunneling microscope, appropriately abbreviated as STM, and the atomic force microscope, which is rightly abbreviated as AFM, to structural problems at the electrified solid-liquid interface is one of the most important advances in electrochemistry over the past decade. These techniques, known collectively as scanning probe microscopy, abbreviated as SPM, are important because they provide a hitherto unobtainable level of structural insight into surfaces in solution. Because the charge transfer or capacitive charging event central to electrochemical reactivity occurs within a few atomic diameters of the electrode surface, in the inner Helmholtz plane, the detailed arrangement of atoms and molecules at the interface strongly controls the corresponding electrochemical reactivity. It is when you look at the Gibbs-Helmholtz equation or Gibbs-Helmholtz layers, there is a layer which forms opposite to the electrode, and that's what is called inner Helmholtz plane. The arrangement of atoms and molecules on that at this interface is what is explained here more precisely in the technique called STM. The focus of this review, which has been used here, is to describe recent advances, that is, from 1991 onwards to the end of 1996, in a span of 5 years, where in situ electrochemical STM and AFM imaging directed towards understanding the process of the solid-liquid interface is concerned, is elaborated with the help of this. The solid-liquid interface will always result in one kind of a charge at the electrode and the opposite charge in the medium. And that enables the capacitor which is formed to hold some charge, or the reverse of this, as we call it, the impedance, which changes once we change the parameters. Now, after understanding what is electrochemical scanning tunneling microscope, after knowing about the introduction, after knowing about the applications, we now come down to the real applications of ECSTM, as we call it in brief. It talks about, or it is able to investigate or carry out these studies for adsorbate layers, or as adsorbate dynamics, as we call it. It also can study metal electrodeposition. It is able to carry out an in-depth study into phase transitions at metal electrode surfaces. Well, typical applications of STMs would relate to electrochemical STM, that is ECSTM, as I said it earlier. Powerful imaging tool it is. By now it is very clear that it gives the best possible images even to the level of single atom. We can go to the atomic level as well. That means it has a very high level resoluting power. It directly visualizes the electrochemical processes in situ and in real space at molecular or atomic levels, as I said. And to reach that level, this is a great equipment which is able to help us in very many situations. Such interfacial electrochemical studies have been dramatically expanded over the past decades. That means the use of this equipment has expanded a great deal, and anybody who is working in the area of electrochemical sciences is making potential use of this equipment. This is able to study the covering areas in electrode surfaces, metal deposition, charge transfer, potential dependent surface morphology, corrosion, batteries, semiconductors, and nanofabrications. Having known so many applications, one can immediately realize the importance of this equipment. Events in the electrochemical data correlate with changes in the topography of the sample surface. Well, the advantage gained from the use of conducting metal coatings and replicas does not come without some drawbacks. That means there are some problems which one faces while using this equipment into many directions. However, we must remember that with these techniques, the STM creates images of the metal coating and not of the original biological material. Thus, the resolution is limited by the nature of the coating procedure and the topography of the grain in the metal surfaces. In fact, to our knowledge, there have not yet been any demonstrations of atomic level or atomic details in biological samples, because those samples have larger molecules and it is very difficult to go up to the atomic levels. But as I said, we do not have any details of the atomic level studies in biological samples prepared by any of the methods. Clearly, procedures for specimen preparation must receive considerable emphasis if the potential of the STM is to be realized for molecules of biologically important materials. Well, many research groups of late have attempted to image biological samples directly without making a replica, because that gives the actual study of the real material. A limited number of biological macromolecules have been imaged with the help of STMs, including that of DNA in vacuum, and in water, of course. Bacteriophage cell sheaths and porine vesicles, but with limited resolutions, have also been studied with the help of this. Model membranes such as Langmuir biodot films of cadmium archidate have also been imaged very precisely. Other researchers abandoned their attempts to image biological materials directly after finding it very difficult to obtain reproducible results. Because, as I said, biological materials have very large molecules, and to get the reproducible results, one was finding it very difficult. It is unclear what the mechanism of the electron transport is through these materials, which obviously one has to do it with the help of STM. Electrochemical STM, 3 electrode system having, in this particular technique, which is called electrochemical STM, are used. The STM tip may also become working electrode as well as a tunneling tip. Need to insulate all but the very end of the STM tip with a Pazion wax to minimize Faraday currents, which can be several orders of magnitude larger than the tunneling current and make atomic resolution unfeasible or even trigger other unwanted electrochemical reactions. This has been shown in this figure, which indicates a working electrode and STM tip, which is close to this. There is a solution, the sample is there. We also have reference electrode here and a counter electrode, which is connected to a potentiostat. And on the other side, we have STM controller. The photograph of this has also been given on the right side of the slide. Imaging and the way we image the structure of electrode surface, that has also been shown here. There are different diagrams indicated in this slide. STM images of gold with 100 plane and electrode surface has been shown here. One is 18 nanometers by 18 nanometers, the other is 14 nanometers by 14 nanometers surface. On the left side, we have STM images of the gold 11 surface, or as we call it, electrode surface. Right side of this has the reconstructed surface of negative charge densities, and on the left side has unreconstructed surface at positive charge densities. The figure on the right, which deals with gold 100 plane, the left side deals with gold 100 electrode in 0.1 molar sulfuric acid at minus 0.25 volt versus saturated calomel electrode, where potential induced reconstruction proceeds. The initially reconstructed surface is being gradually transformed into the reconstructed form. On the right side, the picture deals with the zoom that shows a section of the surface, 3/4 of which has already been reconstructed. One single reconstruction now on the left hand side is seen to grow from bottom to the top of the image. Metal deposition. On applying and potential negative to the equilibrium potential, ER to cathode, bulk deposition of metal takes place. As a nucleation and growth process, deposition of metal preferentially occurs at the surface defects, such as steps or screw dislocations. The two diagrams are shown here. One is STM images of gold 111 surface in 5 millimolar sulfuric acid, which has 0.5 millimolar copper sulfate also before the panel. In A it is given, and during panel B, copper deposition has been shown. The bare gold surface has atomically flat terraces separated by 3 nanoatomic high steps. After a potential step to negative values, deposition of bulk copper occurs almost preferentially at the monoatomic high steps, namely the growing copper cluster are decorating the gold surface defects. STM-based electrochemical nanotechnology, one of the applications to which STM can be conveniently put. This tip has been shown a tool for manufacturing individual atoms or molecules on substrate surface and directing them continuously to predetermined positions. ECSTM tip generated entities are clearly larger than these single atoms due to their low stability to survive electrochemical environments at room temperature. Tip crash method. Surface damage. Use the tip to create surface defects, which then acted as nucleation center for the metal deposition at pre-selected positions. Jump to contact method will also have something like similar method. Surface remains undamaged. Metal is first deposited onto the tip from the electrolyte. Then the metal loaded tip approaches the surface to form a connective neck between tip and substrate. Upon retreat of the tip and applying a pulse voltage, the neck breaks, leaving a metal cluster on the substrate. Continued metal deposition onto the tip supplies enough material for the next cluster. This has been very clearly shown in the diagram given below. Application of STM in SAMs. Electrochemistry can be used to manipulate the adsorbates themselves by electrolytically cleaving the gold SR bond at the surface or at the interface, resulting in a free thiolate and gold. Electrochemical desorption takes place in the reverse phase, that is, RS and gold would accept one electron and will give RS plus gold. This has been shown in the diagram given on the right side. Different thiols have different reductive potentials. Therefore, this will be varying from minus 0.75 volt to minus 1.12 volts. The current potential curves obtained from 4 kinds of tunneling structures from left to right bear platinum iridium tip over thiols, C60 tip over thiols, bear platinum iridium tip over C60, and C60 tip over C60 are shown in the adjoining diagrams. The disadvantages of these techniques. One, the instrumentation is such that it cannot give you very strongly sharp and resolved images. It gives you poorly resolved images, and it gives you instability and drift images which are not very focused. And these drift images are the ones which will not be able to give you very accurate results. And this instability will also not enable one to measure the important terms like capacitance and impedance in a very accurate manner. Well, having understood the importance of STM into a lot of electrochemical processes, we finally come down to, as I said, there are a lot of disadvantages when we use this, particularly for biological systems. We talk about what are the limitations or disadvantages of STM. Making atomically sharp tips remains something of a dark art. That means something which is not that easy. Still, one finds it very difficult in making sharp tips. External and internal vibrations from fans, pumps, machinery, building movements, etc. are a big problem. Slight disturbance when you are using STM in the building would alter the results, and you will never get these sharp images. That is why we always use anti-dampening tables while carrying out studies with this. UHV and STM is not easy to build and handle. That always remains a problem with very sophisticated equipments. The STM can only scan conductive surfaces or thin non-conductive films and small objects deposited on conductive substrates. As I said earlier, the non-conductive surfaces cannot be very precisely studied with this, and that remains a limitation. It does not work with non-conductive materials, as I said, such as glass, rock, etc., or anything that is going to be covering these. You will find it difficult to carry out images with the help of this. The spatial resolution of STM is fantastic. It is excellent. but the temporal resolution is typically on the order of seconds, which prevents STM from imaging fast kinetics of electrochemical processes, and this is one of the very big limitations when we talk about the mechanisms of various reactions, particularly biological ones. So, having studied all this, students, I'm sure you would have appreciated a great deal about the potential of STM and the vistas which this equipment has opened for the electrochemists who are doing research into very many areas like corrosion or batteries or biological related movement of electrochemical processes. We find we can use this in many facets, and let's talk about the gist of this, or let's summarize what we have learned in this module. The advent of electrochemical scanning tunneling microscope has opened up the possibility of studying the structural development of electrode deposits in situ on a near atomic scale, which is extremely important. The principles of scanning tunneling microscopy, the incorporation of electrochemical cells, and the application of such instruments to electrocrystallization studies are reviewed very briefly in the earliest slide. The overpotential depositions of lead and platinum on graphite are used as examples to illustrate the wealth of information which can be extracted through this equipment. The lead exhibits a deposit topology consistent with conventional diffusion controlled mechanisms, while platinum shows much more complex behavior. The ECSTM can only scan conductive surfaces, as I said earlier, or thin non-conducting films and small objects which are deposited on the conductive substrates. It does not work with non-conductive materials, which is very clear. It has been repeatedly said earlier also, and this is one of the major limitations of this equipment. And though that material which is non-conductive, obviously you know it is glass, rock, etc. The spatial resolution of ECSTM is absolutely superb, but the temporal resolution always has a limitation, and it is of the order of few seconds, which poses a very big difficulty when we try to understand the fast kinetics of some electrochemical processes. Thank you very much. I hope you would have understood the topic.